Okay, so we have talked about the basics of biochemistry. So now we're going to actually start putting the pieces together and building the macromolecules. That is, the molecules that living systems are made out of. Now, we have 4 macromolecules. Macro, by the way, means big. So big molecules. Those 4 macromolecules are carbohydrates, lipids, proteins, and nucleic acids. And these are large and complex molecules, and they are often quite diverse. That is, that there are a lot of different kinds of molecules in these categories. And that comes from the arrangement of the components. That is, when we start talking about isomers, building these different functional groups, building these things into different ways. Now, the primary way that macromolecules get complicated is because many of them represent polymers. That is, that they're built out of smaller units that are put together into complicated ways. So, a polymer is a long molecule, a chain of molecules of similar building blocks. The individual components are called monomers, and the molecules themselves are put together into these complicated ways. Now, lipids are kind of an exception, and we'll talk about lipids. Lipids are put together, or many lipids are put together, but not into these long chains. Carbohydrates, proteins, and nucleic acids are long chains of molecules. Lipids tend to be a little bit different, and so there's kind of a little bit of a gray area calling them polymers. Now, we build these polymers up and we break them down. And the fact that we can put them together and take them apart relatively easily means that the cells can manipulate these components. We do that with enzymes, with specialized, generally proteins, that act as catalysts to speed up these changes. One of the things about these polymers is that there is a consistent mechanism for polymerization. That is, that they're put together in very consistent ways. And so that means that the cells can easily take them apart, put them together. Now, what's happening here is we're going to put things together with what's called a dehydration reaction. It involves pulling a water molecule out, and then we can take them apart by taking that water molecule and putting it back in, and this is called hydrolysis. Now, how does this work? Well, you've got 2 atoms, 2 molecules, one that has a hydrogen available, one that has an OH available. So if we take those 2 molecules, we can put them together by removing that H and OH, turning that into a water, and leaving behind a connection between those 2 components. And so that is dehydration, because you're removing water. The opposite is hydrolysis, hydro-water lysis breaking. And we do that by bringing that water molecule in, attaching the hydrogen on one side, the OH on the other side, and the 2 molecules are now separated. Animation of this.
Most biological molecules are very large and are built by assembling small molecules, or monomers, into long chains. The resulting molecules are called macromolecules, or polymers. A process of linking monomers, called dehydration synthesis, involves the removal of 2 hydrogen atoms and 1 oxygen atom to form water. One way this might happen is diagrammed here, where several generic monomers are shown with OH groups that could be used for linking. The animation illustrates the joining together of monomers by dehydration synthesis, catalyzed by a polymerase enzyme, and the reverse process, in which added water results in hydrolysis, catalyzed by a...
Now, one of the things that this does is By varying the different components, varying the different monomers, for instance, we can make a huge diversity of different polymers. And those polymers are going to have different properties. They're going to have different structures. They're going to do slightly different things within the cell. And this is what's creating all of that diversity, that different kinds of things that we can put together so that the cell can do things. And that's because we can build lots and lots of different polymers from a relatively small number of monomers. In the same way that you can make literally tens of thousands of words out of 26 letters, we can, by putting them together in different ways, we can take and make literally thousands of different proteins by putting together the different amino acids. We make different carbohydrates by putting together different sugars. We build different kinds of DNA, or we build DNA in different sequences by putting the nucleotides together in different orders. So what I'm going to do, and I've broken this narration into two parts. I'm going to talk about carbs and lipids, and then in the second part, I'm going to talk about proteins and nucleic acids. So let's start with carbs. Primary function of carbohydrates is as fuel, but we can also use them structurally. We can build with them, and so we'll talk about some of those components that we can use to build with. Now, the monomers of carbohydrates are sugars. So carbohydrates are individual sugars, what are called monosaccharides, sometimes referred to as simple sugars because they are easily metabolized. We can put those together into two sugar units called disaccharides. We can get oligosaccharides. Oligo means moderate or middle, so moderate chains of carbohydrates. And then we can have polysaccharides, many chains of individual sugars. So first thing to do is what is a sugar and how can we identify it? Okay. Well, sugars are molecules that have a general chemical formula or ratio of components of one carbon to two hydrogens to one oxygen. So glucose, for instance, is C6H12O6. Okay? It's the most common monosaccharide, but there are lots of others. Now, when we talk about sugars, those hydrogens and oxygens are attached to that underlying carbon skeleton with one carbonyl and the rest of the oxygens associated with hydroxyl groups, OHs. That means that we can have two different kinds of carbonyls here, aldehydes or ketones, or rather aldose or ketose sugars, depending upon where that carbonyl is located. Those sugars, the most common sugars used in biological systems come in 3, 5, and 6 carbon units, what are called triose, pentose, and hexose sugars. There are also 4, 7, there are a variety of different sugars that may be less common. You'll notice that they come in two varieties. So if we look at the bottom here, we've got hexose sugars, so 6 carbon sugars. Glucose and galactose are both aldose sugars. You notice that the carbonyl is at the end of the structure, whereas fructose is a ketose sugar. Okay? So one of the characteristics of sugars is going to be one carbonyl, the rest of hydroxyls, and that carbonyl then can be either at the end or in the middle of the structure. Gives us some of the categories. Now, these structures are written here in a linear format. So, for instance, at the bottom, you'll notice that glucose has 5 OH groups, and they are written here right, left, right, right, right. Okay, take a look at that. Okay. Galactose, which is a different sugar, is right, left, left, right, right. Okay. You take organic chemistry, you'll learn that there are in fact different hexose sugars depending upon where those carbonyls are located. And there's in fact a mnemonic to remember the relationship. Doesn't matter. Not that important to us. The point here is that those are two different sugars because those structures are arranged in a different place. They have different shapes. And that would not be true if the sugars were in this linear format, okay? But sugars don't stay in this linear format. When they're dissolved in water, they become a ring, okay? And because that's then a three-dimensional structure, right and left actually make a difference because it changes the shape of the sugar. So, sugars actually form in rings. And so, for instance, glucose here, notice right, left, right, right, right. Well, when it gets into water, the carbonyl and one of those OH groups is going to interact. And it's going to form this ring structure. And by the way, note that you can keep track of which carbon is which. They're numbered. And so the one over here on the right-hand side is carbon number 1. The one down in the lower right corner, carbon 2, 3, 4, 5, and 6. And that actually refers to that linear structure. Okay. Galactose, because it has the OH on the other side, would have over here on the left side, carbon number 4, the OH would be above and the H would be below. And because of that, we have a different structure. Different structure, different shape, slightly different properties. So, sugars, 1 to 2 to 1 ratio, 1 carbonyl, the rest OHs, organized in a linear structure, aldose versus ketose, but in water, and that's where we're going to find most sugars, they're going to be organized into this ring structure. Now, we are going to now take these individual monosaccharides and we're going to start putting them together into disaccharides. We're going to form a glycosidic bond, which is a special case of these dehydration reactions. So, there are a variety of these different disaccharides. You will have been probably most familiar with sucrose, which is a disaccharide that comes from plants. You also may have run into maltose or lactose. Okay. These are different monomers put together with these glycosidic bonds. Maltose, for instance, malt sugar, comes from breaking starch down into two saccharide units. And so you get two glucoses together. And what happens is the OH on one side and the H on the other get pulled off into a water molecule, leaving an oxygen behind. And that oxygen is attached to the two different sugars. And in this case, the oxygen is a 1,4 glycosidic linkage. And that comes from the numbers of the carbons on those two glucose molecules. Okay? So carbon number 1, carbon number 4 of the other glucose. Sucrose is the sugar you're probably most familiar because that's cane sugar, that's beet sugar. This is the sugar that plants use to store their food in when they store it as a disaccharide. And sucrose is 1 glucose and 1 fructose. Now you notice that the fructose has a different shape than the glucose, and that's because it has a carbon off of each end, okay? Because the original, the ketose carbonyl was off of carbon number 2, and so when we count those carbons up, okay, it's carbon 2 that we're off of on one corner, not carbon 1. So it's 2 and 4 that we're off of there. Okay, so the point here is that glucose and fructose have different shapes, but they're still going to be put together with a glycosidic linkage. But in this case, it's a 1,2 glycosidic linkage because we're coming off of carbon number 1 on the glucose and carbon number 2 on the fructose. So you see that these molecules are put together, these sugars are put together in consistent ways. That's what we mean by that polymerization and this shared sort of similar chemical reaction. Once again, animation.
Sometimes organisms link sugar molecules in pairs to form disaccharides. Here are several examples. Plants make sucrose by joining glucose and fructose. Sucrose circulates in plant sap, and we obtain it from sugarcane and sugar beets and use it as table sugar. Lactose is formed by joining galactose and glucose. Lactose is the disaccharide that gives milk its sweet taste. Maltose consists of 2 linked glucose molecules. Digestion of starch in a sprouting seed or in the intestine of an animal.
Now, monosaccharides and disaccharides are often referred to as simple sugars, and that's because it's relatively easy for your body to absorb and digest these sugars. This is quick energy. This is one of the reasons why sugar tastes good. Your body is saying, hey, I like that. That's worth getting more of. Right? It's quick energy, and it's energy that our bodies generally aren't that used to. This is one of the reasons why we start to see things like diabetes, etc. Our hunter-gatherer ancestors would not have had a whole lot of exposure to simple sugars. Now, given those simple sugars, they would have gone after them. So you see the Kalahari Bushmen, for instance, going and collecting honey from beehives because that's quick energy, that's good energy. But nowadays, you can just go to the store and get a 5-pound bag of sucrose. And so we tend to get much more exposure to sugar, and that can create a problem. Although, under the right circumstances, that's good energy. For instance, if you've ever done any, serious running, I'm a paddler, you'll see people in like marathons consuming these squeeze packets. And in that squeeze packet is basically simple sugar because it quickly gets metabolized, it quickly gets directed to the muscles, so the muscles have more energy to continue running. Now, the other kind of carbohydrates are polysaccharides, complex carbs. And complex carbs come in 2 varieties, storage and structural. Storage polysaccharides are more condensed ways of storing sugar. And so instead of 2 sugar units, you may have hundreds, long, long chains of sugars that are combined together. This gets us a little bit more condensed, and it's a little more stable than the simple sugars. So storage polysaccharides, when we consume them, okay, this is starch, for instance, it's going to take a little bit longer for our system to break that down and make the simple sugars available, because you got to take that long chain of polysaccharides and break it into small bits. before you can then absorb it into your system. We'll get to structural polysaccharides, but you can build out of sugar too. Okay, so storage polysaccharides. Well, there are a variety of storage polysaccharides. There are different kinds of storage polysaccharides that we find in algae, for instance. But the most familiar storage polysaccharides that we're going to run into are going to be, and so these are going to be starch. And these get formed into relatively insoluble starch granules that are stored inside specialized cells. So for instance, in a potato, you'd have a whole bunch of starch granules inside those individual cells. Okay? Simplest form of starch is amylose.
Produces this.
Amylose is essentially a single chain of glucose monomers. Long, long chain of it. But we also get other kinds of long chain storage polysaccharides in plants. You might be familiar with another somewhat branched version called amylopectin. You're probably familiar with amylose versus amylopectin, however, because of the different properties. For instance, rice. Long grain rice has relatively more amounts of amylopectin, whereas short grain rice has more amylose. What this means is that, okay, you cook rice. One of the things you're going to do is you are going to gelatinize those starches. They're going to be soft. You get, for instance, take out Chinese, and you've got that rice, that sticky rice that you're eating. Well, you put the remainder in the fridge. You get it out in the morning, and it's kind of crunchy and hard. And the reason is that the starch has crystallized. Okay? Long grain rice will crystallize more than short grain rice, and that's because of the different kinds of starches present. If you've ever watched somebody make sushi, by the way, sushi is not about the raw fish. Technically, sushi refers to the rice. Okay, su is Japanese for rice. Shi is, I believe, sweet or sugar, because they put a vinegared, sugared solution onto the rice as they cool it down. But the thing here is that a sushi chef will take that rice, that hot rice, and they've got this big bowl, and they will fan it, and they will flip it, and they will cool it very carefully so that it doesn't get hard and nasty. Right? What they're doing is they're manipulating the starches. Now, in animals, we also have storage polysaccharides. That is, that we will store sugar in our muscles in a form called glycogen. And the difference between glycogen and starch is glycogen is many-branched. It's all still glucose, but it's glucose chains that branch and branch and branch from each other. In marathon running, and this doesn't happen nearly as much as it used to, but in marathon running, at about 20 miles, people would hit what was referred to as the wall. Okay? In fact, in the Boston Marathon, one of the oldest continuously operating marathons, there is a hill just at about this point, and it's referred to as the wall. It's not a particularly steep hill, but it's the point where your glycogen reserves start to run out. Right? If you are properly fueled before the race, you will start to run out of energy by about 20 miles. And this is called bonking. Okay, yeah, I know. Bonk can mean many different things. In an athletic context, bonking means that you've run out of glycogen. And so you've run out of energy, and suddenly things become a whole lot harder. Nowadays, people don't run into the wall because it used to be that people didn't eat anything during a marathon. Nowadays, people will consume those little goos, those carbohydrate packs, quickly absorbed, quickly replacing some of that energy. And so people don't bonk. So in your muscles, you store glycogen. You also store glycogen in your liver. Say your body starts to run out of blood glucose. Well, one of the things your body's going to do is it's going to send out, okay, blood glucose levels drop. Okay, your body sends out a signal and says, oh, release glucagon. Okay, and what glucagon does is it tells the liver, oh, take some of that stored glycogen, chop it up into sugar, ship it out into the bloodstream, and blood glucose rises. Glucagon, by the way, is the opposite. It's a different molecule, but it operates opposite to insulin. Insulin tells your cells to suck glucose out of the bloodstream, so it drops blood glucose levels. Glucagon raises blood glucose levels by telling your cells to release glycogen or release the glucose stored in glycogen. This is also why, if you take a look at hunter-gatherer cultures, men often are doing the hunting. And one of the things that they will do after having made a kill, and this is found in Kalahari Bushmen, it's found in Amazonian Indians, it's found in a whole bunch of cultures. They will part the animal out, okay, take the haunches off, big major muscle groups, wrap it in the skin and carry it back. But they will share out the liver and either cook and eat or eat the liver raw right there at the kill. And the reason is that you may have expended a whole lot of energy. Well, where in that body are you going to get quick energy? Glycogen in the liver. And also, the liver isn't something, it's an organ meat. It's probably not going to survive. It's fairly delicate. It's not going to survive getting carried back to camp. And so, these things make sense.
Polysaccharides are polymers, long chains consisting of hundreds to thousands of linked monosaccharides.
Glycogen stored in liver and muscle cells and used to as an energy storage mechanism. Right? You're going to release glucose when it's needed. Now, the other kind of polysaccharide is a structural polysaccharide. And this is relatively inedible, relatively insoluble structures made out of sugar. And probably the most common of these is cellulose. Cellulose is the major component of plant cell walls. It is a long, stringy molecule, and the cells make them and use them as fibers, essentially, to build the cell wall. Now, why would a plant want to use sugar as a building block? Well, it turns out, what is a plant doing? It's doing photosynthesis. What is it making? Sugar. So actually, it makes sense. Sugar is cheap for the plant. So if I can make something that's structural, I can make, I can use this cheap material to build with. Now, cellulose is made out of long chains of glucose. Okay, so that raw material. But it doesn't dissolve, and it's not readily eaten, and it's because the cellulose is put together with a different structure. Okay, when we take a look at glucose, the OH on carbon number 1 can come off either below or above. Okay, 2 places. This is called the alpha conformation or the beta conformation. In glycogen, or any of the starch polysaccharides, we're going to have an alpha 1,4 glycosidic linkage. Okay? So if you take a look at the top row of glucoses, all of the OHs on carbon number 2 are down. But in cellulose, we're going to use a beta 1,4 glycosidic linkage. And that's going to put those OHs off of carbon number 2 on opposite sides. Okay, take a look at that. And that structure is different enough that the enzymes, that the tools we use to break glucose down won't work on cellulose. And so cellulose is a convenient structural component because it's not something that's easily broken down. It can't be decayed. Right? One of the few kinds of organisms that can break cellulose down, that have cellulases, are fungi. And this is one of the reasons why you see mushrooms, for instance, growing out of old logs. Okay? It's because they can access that sugar. So, point here is that cellulose is a structural polysaccharide. It's a way of taking sugars and building them into a convenient structure, but one that isn't going to be easily broken down by other organisms. So it's stable. And plants have utilized this to make their cell walls out of. The other place, and so this is just explaining that. The other place that we will see structural polysaccharides, or at least commonly, and there are other structural polysaccharides out there. There's some in various kinds of algae, in different kinds of protists, etc. But the other common place, the other common kind of structural polysaccharide that we'll run into is something called chitin. Okay? Chitin is nitrogenated, so it's there's some nitrogen associated with it's basically a modified sugar molecule, and that then is going to make a light and strong structure, but using the sugar as a base molecule. Chitin is found in the cell walls in fungi and also in the exoskeleton of arthropods. So insects and crabs and that sort of thing. Okay, so carbohydrates, food and building material. Food in the form of simple sugars, monosaccharides and disaccharides. Storage of food in the form of storage polysaccharides, amylose, amylopectin, collectively referred to as starch, and then glycogen in animals, as examples, and then structural polysaccharides being used to build permanent structures, but out of a base sugar molecule. So that's carbohydrates. The next macromolecule to talk about are the lipids. Now, the lipids are, unlike carbs, proteins, and nucleic acids, where the monomers are all fairly consistent. Lipids are not built out of necessarily the same bits, because lipids are not united by what they are, they're united by what they aren't. What do I mean by that? Well, lipids are hydrophobic molecules. Basically, this is the category of, all of the hydrophobic molecules, we're going to call them lipids. Okay? They aren't really true polymers in the sense that they're not long chains. They are, however, in many cases, built out of other molecules with dehydration reactions. So there are some similarities. Okay? Lipids are often going to contain hydrocarbon regions, that is, lots of carbon and hydrogen components, because those are nonpolar. And they include fats and oils, okay? Phospholipids, which are modified fats, steroids, waxes, etc. We'll really are going to talk about fats and oils, phospholipids, and steroids. So let's start with fats. Okay? Fats are composed of two base molecules, a glycerol molecule, which is a three-carbon alcohol. So 3 carbons linked together with an OH off of each of them, and fatty acid tails. Fatty acid tails are a carboxyl group at one end attached to a long chain of carbons, which are in turn attached to hydrogens. So this is what it looks like. Okay? The glycerol is over there on the left, and the fatty acids are these long chains of molecules. Okay? Generally, fatty acids consist of 12 to 14 to 18 carbons in a row, but they're going to have that carboxyl at the top, that COOH group. And so an OH off that carbon is going to combine with an OH off the glycerol, remove the water, dehydration reaction. This, by the way, is not a glycosidic linkage. It's called an ester linkage. Yeah, go talk to the chemists. Okay? But that's what we call them. By the way, the molecule at the top here would be a monoglyceride because it has one fatty acid. You can get them also as diglycerides, or the one at the bottom is a triglyceride. If you've ever been to the doctor and got one of those fasting blood works, one of the things that they will tell you is your triglyceride levels. They're talking about how much fat is floating around in your blood, reflecting basically diet, activity, genetic factors.
Butter, lard, margarine, and salad oil are composed of lipids called fats. To make a fat molecule, 3 fatty acids bind to a molecule of glycerol. For this reason, fat molecules are technically called triglycerides. Fat molecules do not mix with water because they have 3 long nonpolar hydrocarbon tails. Cells use fats for energy storage because the tails hold more potential energy than other biological molecules. The fatty acid tails in a fat can vary in length. A very important characteristic of fats is the number of double bonds in the hydrocarbon tails. Fats that contain only single bonds are called saturated fats. Fats containing double bonds in one or more tails are called unsaturated fats. Unsaturated fats tend to be liquid at room temperature. Vegetable oils are examples. Saturated fats, like butter and lard, are solid at room temperature. Saturated fats in the diet can lead to heart disease, while unsaturated fats are safer.
What can we say about fats and oils? Well, these are hydrophobic, so they're not going to mix well with water. They're hydrophobic molecules, and they differ in chemical properties. Okay? That is that the fatty acids can be different depending upon what kind of fat we have there. So when we talk about fats, we often talk about saturated or unsaturated fatty acids. And this has to do with the fatty acid tails. Saturated fatty acids have single carbon bonds between all of the carbons, and therefore the maximum number of hydrogens that can be attached. Unsaturated fatty acids have one or more double carbon bonds, and so for each double carbon bond, we're going to have 2 fewer slots to attach hydrogens to. So they are unsaturated. They don't have the maximum number of hydrogens. Now this has a number of consequences. Saturated fatty acids are straight. That means that the fatty acids, the triglycerides, can easily line up together, and therefore they stay stable and solid at higher temperatures. Saturated fats tend to be solid. Saturated fats are animal fats. And so butter, lard, if you get a steak, the white fat that's in the meat, that intramuscular fat that is actually tasty. Fats, by the way, fat is flavor. One of the reasons is because what's the purpose of fat? Well, one of the primary purposes of fat for us is high energy. It's an energy storage molecule. And so fats contain about 2.5 times the concentrated energy as either proteins or sugars. And therefore your body says, hey, that's lots of good energy. Get me more of that. That's why fat is flavor. So saturated fats are animal fats, and they tend to be solid at room temperature. Unsaturated fats, on the other hand, have double carbon bonds. And under normal circumstances, the extra hydrogens are going to be on the same side. So that you're going to get a cis condition. Remember we talked about cis trans isomers? Well, here we get a cis condition. And what that does is it forces the chain into a kink. Okay? Unsaturated fats are oils. These are generally plant fats. And just remember, oils are kinky because the kinked tails of the unsaturated fatty acids mean that they don't easily line up together, and therefore the fat stays liquid at a lower temperature. So, fats are saturated, animal fats, solid at room temperature. Fats can be oils where they're unsaturated and plant-derived by and large, and they're liquid at room temperature. And that's because you have different kinds of fatty acids in those organisms. Now here's an interesting thing about the situation. Okay? People started noticing that diets high in saturated fats were associated with certain kinds of health conditions. Okay? People who ate lots of saturated fats often had higher rates of heart disease. If you look at, for instance, the Mediterranean diet, fish and olive oil. Okay? You'd go to someplace like Sicily and you'd go to a small village and there might be 2 or 3 people who are 100. And so by the 50s, people started thinking, hey, we want to avoid saturated fats. Now this corresponded to a couple of other things that were happening in the world. One of them was that they'd figured out how to hydrogenate vegetable oils. That is, chemically alter the vegetable oils so that instead of being liquids, they were solid. This had a number of knock-on effects. One, it was cheaper. Butter was expensive. Corn oil was cheap. If you could turn corn oil into the same consistency as butter, dye it to look like butter, and maybe flavor it to taste like butter, you could replace it. So margarine came around. Also at the same time, this was sort of the post-war, a lot of people were working. we had the development of sort of industrialized food. Hydrogenated oils are more stable. That is, that they won't go rancid, they won't go bad as rapidly. And therefore, you could use cheap hydrogenated oils to replace expensive and unstable animal fats. So, through the 60s and 70s, we had this proliferation of hydrogenated vegetable oils in all sorts of foods. Now, the problem is that that chemical change, what you're doing is you are taking the kink and you are changing the cis condition hydrogens to trans condition hydrogens. So you're essentially taking the kink out of that fatty acid. You're not adding hydrogens, you're just rearranging them. So you're not making it saturated. It's still an unsaturated fat, but it is now a trans fat. And starting in the 80s and 90s, people started recognizing that, you know what, trans fats aren't a good thing. If you take a look at what's actually happening to people when they consume a diet high in saturated fats, you can take a look at blood chemistry. And there are two molecules that carry fats. Remember, fats are insoluble in water. What's your blood made out of? Essentially water. So you have to have proteins that carry the fats around. And those proteins come in two varieties, what are called low-density lipoproteins, or LDLs, and high-density lipoproteins, or HDLs. LDLs are the normal carrying molecules. HDLs are the sort of the cleanup crew. So what happened when you had a diet high in saturated fats was it didn't affect the HDL level, but a diet high in saturated fats tended to increase the LDL level. On the other hand, a diet rich in unsaturated fats tended to decrease LDL levels and maybe had an effect a little bit on the HDL levels. But when we look at what trans fats do, trans fats give you a double whammy. They increase the LDL and they decrease the HDL. So they increase the bad fat, decrease the good fat. And so this is why trans fats are now kind of a bad thing. But they're still really important because they are sort of trans fats or materials like them are going to be important for industrialized food. The ability to, say, make cookies in big quantities in a plant and then ship them all over the country and have them sit on the grocery store shelves and not go bad. One of the sort of the knock-on effects of removing hydrogenated vegetable oils from our food supply, yes, it decreases trans fats, but what they replaced it with was palm oil. And so it's had actually a quite serious effect in Southeast Asia with the proliferation of palm oil plantations, basically chopping down the jungle and replacing it with palm oil plantations. And this has hit orangutans and the Sumatran rhino and a whole bunch of animals that lived in those jungles pretty hard. So it's not all, yes, replacing trans fats is a good thing, but the knock-on effects are not all good. So fats, energy storage, also food reserves. By the way, having fat is important, at least evolutionarily. Fat people survived famines because if you stored fat, you had reserves when there wasn't food around. Adipose tissue also is important for insulation. Take a look at, say, a walrus. They insulate with a layer of fat. But it's also things like body contours. Um, breast tissue, for instance, is primarily fat. And so somebody who, a female who has a very low body fat percentage is also not going to have curves. It's just the nature of the beast. So fat is important. Fat is actually vital. Without fat, you actually get sick. And so we all operate with a certain level of fat. Too much fat, though, can be a problem, and that's largely because of our diet, the availability of food, and that sort of thing. Now, these are what are called neutral fats. We're going to take some neutral fats and modify them in a way to make them useful in a different way. And that is with these molecules called phospholipids. A phospholipid starts with the same basic structure, a glycerol, but instead of 3 fatty acids, we're going to take 2 fatty acids and attach them. And to the other OH on that glycerol, remember it has 3 slots, we're going to put a phosphate group and some other stuff. Now, what this does is it makes sort of a schizophrenic molecule. The technical term here is amipathic. That molecule has a hydrophobic end and a hydrophilic end. The hydrophobic end is the phosphate end. The hydrophilic tails on the other side, the hydrophobic tails on the other side are the fatty acids. Now, why is this important? Well, this is going to be the basis of cell membranes because phospholipids will self-aggregate into what's known as a phospholipid bilayer. That is the hydrophobic tails toward each other, away from the water, and the hydrophilic heads out toward the water. Okay? And so when we start talking about cell membranes and how cell membranes work, we're going to start with this phospholipid bilayer. This is also, by the way, why, for instance, you take a look at formula. Formula has a whole bunch of specific kinds of fats in it because these are important for building cell membranes, and cell membranes are necessary to build brain cells. And so this is why, it's either nurse, that is using uh, uh, the mammary glands, making the appropriate components, or with something like a formula, replacing the um, uh, the breast milk with an appropriate replacement with all of the necessary components, or most of the necessary components. Okay, so what that means is that phospholipids are going to be really, really important for building cells. And so we'll talk about cell membranes and the structure of cell membranes and the function of cell membranes, and it's intimately associated with these phospholipids. The last thing I'm going to talk about are a completely different kind of lipid, and these are steroids. Steroids are messenger molecules, so they're hormone molecules, and they're built off of a molecule called cholesterol with additional functional groups. And so cholesterol is actually necessary. This is one of the reasons why low body fat percentages is actually kind of an issue because it starts to screw up your body's communication system. We will talk about steroids in a couple of different contexts, but it's basically these are communication molecules. You're probably most familiar with testosterone and estrogen as steroids, but other things like cortisone or cortisols, corticosteroids, also exist. And these are all built off the same basic structure. Okay? That's a cholesterol molecule. And steroids are built out of this component. So Lipids, diverse group of hydrophobic molecules with some general characteristics, but not everything looks the same. And it's because it's diverse. Okay? So, next part, part 2, I'll cover proteins and nucleic acids. Another animation.
Disaccharide.
enzyme.